awake and alert and inquisitive this whole time. We're live on YouTube, so I think, Ehud, you can go whenever you're ready.
Okay, I'll start for some reason. Oops, what's going on here? Okay, good. So yeah, today I'm going to talk about scrambling in not only in quantum circuits. I want to make a focus on quantum circuits. I'll talk about maybe more generally and why people are interested in scrambling recently a little bit, and then turn to some interesting approaches to compute scrambling dynamics in quantum circuits. So let's start. What is scrambling at all? What do we mean by scrambling? So if we have quantum many-body time evolution, we know that it generates entanglement. So here, we point to, here you see the special case of say just two qubits, and it could be a C0 gate or any kind of generic gate on two qubits will generate entanglement. And if I take it, if I apply some network of unitaries, either a Hamiltonian dynamics or just a quantum circuit on a generic state, on some state, on any state, even a product state, eventually I'll get a super entangled state. And that means that if I encode information initially in some local degree of freedom, that information will be hidden in a huge number of non-local parameters defining this many-body superposition, right? So I transformed or encoded local quantum correlations into extremely non-local ones that are not measurable. And again, this unitary U could be a generic circuit, or it could be a quantum Hamiltonian, as long as that Hamiltonian is sufficiently generic. And maybe it's different in the case of many-body localized. We can talk about this. We get this extremely scrambled state. And the essence of thermalization, basically, is that the wave function becomes essentially identical to a random state after a sufficient evolution. Well, identical to a random state up to some constraints imposed by conservation laws. So that's basically why we thermalize to a particular temperature and not to infinite temperature. But up to that, we're in a random state in the allowed conserved subspace of the Hilbert space. Now there is a comment required here that when we say identical to a random state, usually if we're physicists, we say that it's identical if all observable expectation values are the same. But recently there has been a lot of interest in quantum circuits in the community of quantum computing. And for this community, identical is a more subtle word. And in order to be identical, well, then there are different degrees of being identical. And one has to look at the full distribution of measurement results, for example, of a particular operator you're going to measure. And you can ask whether it's identical only in first moments of this distribution, only in second moments of this distribution, and so on. So there is a more subtle meaning to what we mean by identical. And it also, and if we want to be identical to higher orders in the distribution, we also need to usually let the system evolve for more time. So there are different thermalization times for being identical at different orders. So this is like a small remark on, but for most physics purposes, identical simply means identical at the level of expectation values of observables.
When you say this physics definition, would that be like local observables, or do you allow any?
Okay, yeah, that's another point. Yeah, and usually in this physics definition, it would be local observables. That's right. And in fact, we cannot, there is no sense in, if we're talking about any kind of observable, then there is almost no meaning to what it would be in random. That's right. And so yeah, for example, if we are talking about any kind of observables, then they might not even thermalize. They could be, for example, eigenstates or projections on eigenstates and so on. Right. So when I say identical for physicists, it means sufficiently local observables and in the sense of their expectation values. Okay, so now what is operator growth and out of time order correlation? So what I gave you here was in the sense of states. Basically, it's Schrodinger evolution of a state. And I said the state becomes more complex and more entangled, and quantum information in the state is being delocalized. But of course, we also have an identical perspective from the Heisenberg picture on the time evolution of operators. So if we look at the time evolution of a simple local operator, like, for example, Pauli spin operator, Pauli sigma matrix X, by some many-body evolution, if the evolution is generic, it will transform this single Pauli operator to gradually more complex superpositions of strings of Pauli matrices. So this is an example here of a string of Pauli matrices. And in principle, the operator space, I can think about it. And by the way, I can describe this evolution similarly to Schrodinger evolution by thinking of the operators as vectors and then super operators, which I can call the Liouvillean acting on them. So I can describe this in terms of the action, of a super operator, which is, say, the evolution operator generated by a Liouvillean. And the Liouvillean is a super operator that basically defined by this action. Sorry, the Liouvillean is defined by the commutator with X, right? The Heisenberg evolution. And what it generates now is, just like in states, it will generate more and more complex superpositions in terms of natural basis of operator space, which in the case of qubits, that natural basis is a string of Pauli matrices, which spans the operator space. So I'll get increasingly more and more complex strings that will, if I start from a string on one that includes a non-trivial Pauli matrix only on the site I, now I'll get strings that include more and more non-local Pauli matrices of different sites. And
I think we lost the connection.
I think so. I messaged him, but I'm not sure if it's his internet or.
Hi, do you hear me now?
Yes, welcome back.
Yeah, actually, I think there is, the internet in my house fell. I don't know what happened. I'm now using my phone to tether internet. I hope it'll work.
Wow.
Yeah, sorry. I don't know what happened. Let me just charge my phone because it's also close to,
Mm.
okay. Hope it will work. Let me now start mirroring the screen. I don't know what happened. Why it's not working? Sorry. No, I need to share screen. Share. I'm actually not sure when this happened. So let me know if I come back in the right place. Yeah, I have no idea where this happened. I was talking and then I suddenly noticed that I was, I guess, did you, well, I talked about the complexity of the operator. Did you hear that? Yeah, and the fact that the Pauli strings become larger and larger in space. And the question is how we can quantify this complexity of the evolving operator. And one measure is the size, but what is a kind of correlation function that would measure the size of the operator, okay? And why at all we would want to do that. So I'll explain, I'll give motivations in a second, but one reason for looking at, sorry, I'll give motivations in a second, but the correlation function that would capture the size, one correlation function that would give a measure of the size of the string is the so-called out-of-time order correlation. And the idea of that and why it would give the size is very simple. So let me explain. So first of all, definition of the out-of-time order correlation. I have two operators, say at two different sites, AI and BJ, site I and site J. And I look at the commutator between A at the time t and B at time 0 and square the commutator and look at the expectation value of that. Okay, so it's like the expectation value of the square of the commutator. If you know Lieb-Robinson bounds, it's really the same correlation function that occurs in this Lieb-Robinson bound. Now, as a note, it's very hard to measure this. It's not a correlation function that's easy to measure. You can think about why, because, well, it has A of t appearing twice here and not right by each other, which means that the unitaries don't, the two unitaries on the two sides don't cancel each other. You really need to propagate the system forward in time and backward in time, forward in time again, and backward in time again. And that's why it's called an out-of-time order correlation function. It's not a usual response function. I'll show that in a second a little bit better. But why does it measure the size of the operator? Well, the reason, let's, as an example, take AI to be just the X Pauli operator at site I that we propagate for some time, okay? Maybe to make it short, let's just look at this figure. Forget about everything that's written here. This is the X operator. And now we propagate it with the unitary evolution. Let's assume that there are unitary gates acting on it. But the unitary gates are local, so they act only in nearest neighbors. So they can't give me a string that's larger than what occurs inside this light cone, right? This is what is going on here. It's growing, but even in this light cone, it's changing all the time, right? It can become more and more complex as a function of time. Now, but let's say it's kind of dense and grows within this light cone all the time. Now, I want to measure the size. How I would measure the size, everything outside of this light cone is only identity matrices. And inside this light cone, I have all sorts of stuff, right? All different strings. So what I'll do is I'll put a probe operator at some site j. And that probe operator could be z, for example. Now, z commutes with the unit matrix, but it doesn't commute with x and y. So if I take the commutator with x or the commutator with y, it'll be another Pauli matrix. Squaring it will give you 1, right? So I'll start getting, so if z is outside of the light cone, I'll get 0 for this. And if it comes in to the light cone, if I take this other side j, sorry, into the light cone, I'll start to get something of order 1, right? And so what I expect to see is as a function at different times, so as a function of j, I'll look at this correlation function, it'll be something of order 1 and it will decay to 0. And if I go to later time, I'll see something like this, right? I'll see a front. And this measures the size of the operator because the region where it's non-zero is basically the size of the operator, okay? It's where the operator has non-zero strings, non-trivial operators in these strings. Now, you've probably heard that this out-of-time order correlator is related to chaos in some way. So let me explain how it's related to chaos. Well, one way to explain it, which is maybe the original way to explain it back to 1969, for single particle physics at least, is that take this commutator squared between two non-commuting operators between x and p of a single particle, right? Now, if I take the classical limit of this commutator, we know that commutators become Poisson brackets. It becomes the Poisson bracket between x and p, which is just dx at time t, dx at time 0 squared. So what we get here is the sensitivity to the initial conditions in the classical system. How x at time t depends on on this change of x at time 0. And if this grows, this means that there is an exponential sensitivity to initial conditions, right? So the classical limit of this single particle autark out-of-time order correlation really does go to exactly this chaotic definition of sensitivity to initial conditions. So can we make this more general for our quantum system? Well, yeah, one way we can think about it is we can think about it more generally in the framework. Yes.
There is a subtlety here, which this specifically is for the OTOC where they're canonically conjugate pairs, right?
Yeah. It's a very, very special correlation. I want to make this a little bit more general in the next slide. I mean, still a bit, heuristic, but slightly more general. So I want to remind you of general theory of linear response in quantum systems. So the response of an operator AI, or the expectation value of the operator AI, that's important to a perturbation with some operator Bj at time t equals 0 is this response function. Chi is set by this response function, chi AB ij, right? This is the response function. And this response function is, right, right, this is the retarded response function. It's exactly the expectation value of A after applying a delta function perturbation with B at time 0. Okay, so which is what we want. And so you can ask, well, isn't that measuring exactly the sensitivity to an initial change, the size of the response? Well, no, and the reason why not is because we're measuring the expectation value of A. And what does it mean? So suppose we're close to some classical limit, then let me calculate the expectation value. This expectation value is a sum over classical paths. And to lowest order in the semi-classical limit, it's just sum of classical paths of the system that starts with some fuzzy initial conditions. And the fuzzy initial conditions are basically due to the wave function there is a quantum wave function in the initial conditions. So each one of these classical paths will give me a value for AI of t in this classical system, right? And this is how it will evolve. And I now in red drew here the expectation value. Now the expectation value will have a bump because of the response to BJ. But then all these classical paths will continue to evolve. And if the system is chaotic, well, they'll basically forget their boundary condition because they'll start to oscillate wildly and very differently because they're chaotic. So the fact that they're chaotic means that they will forget their initial condition and the fact that I had a perturbation, and they just oscillate wildly. And when I sum over all of them, eventually I'll get zero. And that's why after this bump, I'll get some decay, usually, right? So this decays, and it doesn't tell me anything about the, I need something that, by the way, so these classical paths are again described by a classical response, which is just a Poisson brackets between these operators B and A. So regardless of whether they're canonical conjugate or not, it does describe the response. But now you can imagine if I want to measure these deviations, then I don't want to look at the response function expectation value. I want to look at the sum over the squares of the differences. So I want some negative and positive contributions and which add to zero. So in that's another way to understand it. And again, some kind of semi-classical limit, okay, which is more general in the sense of response. Now you can ask again, okay, so in this classical system, we had an exponential growth of this autok, and the exponential growth is set by some coefficient, some exponent called the Lyapunov exponent, which is critical to this classical chaos. And you can ask, is that also true in quantum systems? Do we expect to see that generally in quantum systems? And the answer is, well, we don't know if always, but there are certain cases when we know it will be the case. So one case for sure is a semi-classical system. So one way to see it is, that's another way to view the autok is we're looking at operator evolution. Operator evolution in quantum mechanics is basically the Heisenberg equation of motion. The analog of that, as I said, in classical physics is the Liouville equation. The Liouville equation, which is just the exact analog, operators in quantum mechanics map to distributions in phase space in classical physics. And in the classical physics, we see that this distribution grows and becomes more and more complex while maintaining its volume, Liouville's theorem, but it becomes more and more complex, so it practically takes more and more volume of the phase space. The initial condition cannot be the distribution. If we have quantum mechanics, if we quantize this, the initial distribution cannot be more resolved than h bar, right? Because this is the basic volume in phase space. And then it would grow to the maximal allowed volume in phase space, let's call it S max, and maximal entropy of the system. And how long will it take it to grow to maximal entropy? Well, it grows by h bar times e to the lambda LT. So the time scale it will reach S max is 1 over lambda L times log of S max over h bar, okay? And in classical systems, in semi-classical systems, that maximal entropy I can reach is much larger than h bar. And therefore, I'll see a prolonged exponential growth. But if this maximal entropy per degree of freedom is not much more than h bar, for example, if we have just spin half systems, so the maximal entropy is just log 2, then it's not clear why we would see this kind of prolonged exponential growth. Okay, but there is, even if we don't have that per se, we can have kind of a slightly more general notion. So let's take as an example, and my claim is that if we have weak interactions or large n, large number of local degrees of freedom, that's another way to get a prolonged exponential growth. And an example of that is, say, let's take interacting fermions and consider the growth of the operator C dagger. And now we need another operator to probe its growth. So I take some non-conserved operator like the density wave at wave vector pi. It's just an operator I picked. I need something that's not that doesn't commute with the Hamiltonian. So this is the operator, and again, it's the same point. I start the propagation of C dagger I. It becomes more complex, and I want to probe how many non-trivial strings of this operator occur in this light cone. So let's look more closely at what is the evolution of C dagger in a time step. So roughly speaking, the evolution of C dagger in a time step is, if the time step is small, it can either stay, right? Of course, nothing can happen to it. I just expanded the evolution operator, right? Or it can go left or right times I delta t times j. That's just the hopping, and it doesn't make the operator more complex or larger, right? If I had only hopping, nothing would happen. It would, I mean, the autalk will not give me any change, right? Because I'll always have just a single C operator. But luckily, I also have interactions, and the interaction basically turn a single C dagger into a C dagger, C dagger. So, you know, roughly speaking, I create a whole excitation, particle, right? So I create, you know, one type of excitation, which here I draw in red, and another two that I draw in blue. And to help me draw it nicely, I need U to be small. So if U is small, I can draw a nice tree. You know, most of the time, the quasi-particle just propagates, and every once in a while, it splits into 3 new operators, okay? And then so on and so on, right? So that's how the operator, so the operator looks like a tree structure. And what the out-of-time order correlator does, it basically counts the number of branches in this growing tree. And, you know, in a growing tree, it goes like e to the lambda L t. With lambda L, in this case, you can easily, you know, do a very, very quick calculation from this, and you'll see immediately that it's about U squared over J is lambda L, or maybe nicer to write it as the dimensionless interaction constant squared times J. Okay, and yeah, it's small in some sense, right? So in this weak interaction limit, I'm fine. But of course, this will not go on forever. It cannot go on forever. This exponential growth can continue until the branches are basically dense in this light cone. If they're dense in this light cone, it can't grow more, right? I cannot go outside of this light cone for the reason I said, or leave Robinson bounds, or whatever you want, right? I cannot go out of this light cone. But inside the light cone, so now how long does when does this stop? When do I become dense in the light cone? Well, it's when this number of branches become the maximal number of branches that fit into this light cone. How much fits? Well, the size of this light cone, the linear size of this light cone is 2 times, it's 1D. So just the size of this light cone is 2 times the velocity. I call it butterfly velocity, but it's just this maximal velocity, 2 times the velocity times t over h bar a. That's and a is the lattice constant. This is the linear size, but then I allow n degrees of freedom per site. So it's times n, right? Because I can have branches on top of each other going in kind of in another direction, which is the flavor direction. So the total number of degrees of freedom tell me what is the total number of branches. So when this goes to this size, I'm done. So you see, I can rewrite this nicely as n times 2j t scrambling over h bar. And this thing is just the maximal entropy that I can reach at time at the scrambling time. So this defines the scrambling time. By the way, this nice analysis is found in this paper, so you can look at it. And they do some numerics to show that it works. So now I can solve this equation for the scrambling time, and the solution to good approximation is that now t scrambling is equal to 1 over lambda. You can solve it yourself, log nj over h bar lambda. And sticking in lambda we found before, it's j over u squared times log of n over u squared. So you see that this is much larger than lambda if either n is large, and then we have a large log here, or even if n is order 1, if u is small, right? And then if that's the case, then the time it takes to scramble is much, much longer than the inverse Lyapunov exponent, and we'll see a prolonged exponential growth. Okay, so that's another way to now one can ask, okay, is there another regime where it will happen? And there is a nice conjecture. If this formula is general and holds, which is not clear, but let's say this formula is general, then let's go to small temperatures. If I go to small temperature, then I can use another result, which I didn't mention, but I'll tell you about it in a second, which places a bound on the Lyapunov exponent. And the Lyapunov exponent, because of quantum mechanics, cannot be larger than 2 pi t over h bar. Okay, so if that's the case, then we can bound the scrambling time and say that it must be larger than 1 over lambda, and replace this lambda by its largest possible value, 2 pi over t at low temperatures. And that means that at sufficiently low temperature, we're again safe. This log becomes as large as we want compared to So then it will always, this log becomes as large as we want. It grows logarithmically, of course, but even for n of order 1, then we can have prolonged exponential growth. So that's the hope, that if this is the case, then it's very generic, at least in low temperatures. And the result that I'll just skip and go through quickly, I'm not going to place a lot of focus on this. Famous result by Maldacena, Schenker, and Stanford. I forgot to write the reference. Journal of High Energy Physics, I think, 2016. And that places a bound on chaotic dynamics. And the intuition for this bound came from looking at scrambling by a black hole by using ADS-CFT correspondence, and and they found that black holes actually have scramble at exactly this rate, and which is the fastest possible rate. And that's why they're fast scramblers. And for this reason, there was a lot of recent work on quantum models that saturate the bound. And probably the most famous example is so-called Sachdev-Yeki-Taev model, which is not the focus of my talk here, so I won't go into it. If you have some questions, I can answer. But it's basically a model of interacting fermions with no spatial structure that you can then map at low t to at low t. You can map it to a solvable field theory in 0+1 dimensions. It maps to essentially solvable field theory in 0+1 dimension for any temperature, but it gets a very simple and nice structure in the low temperature limit, where it becomes dual to a black hole in ADS2. So this is kind of maybe, if you want, one of the reasons that people started to study these kinds of correlation functions, because of the relation to quantum gravity and quantum black hole physics. Another is that extreme importance of scrambling, as you will see in what comes, in quantum information in quantum circuits, understanding coding of quantum circuits and so on. That's another reason. A third reason is that people believe used to believe that there is a relation between, well, probably true, but the relation is more complicated than we thought, a relation between chaotic dynamics or this scrambling physics and the emergent hydrodynamic transport properties in our system. So if we want to learn how to calculate the hydrodynamic properties, we have to understand this process of chaotic dynamics, which generates the effective dissipation that gives rise to dissipative hydrodynamics, diffusion, right? So you know, the quantum time evolution is unitary, but at long times we know that we get only effectively hydrodynamics, classical hydrodynamics describing transport of some conserved quantities. How does this irreversible classical dynamics emerge from unitary quantum evolution? The way it emerges, we now understand, is because information is lost because of scrambling, and that loss of information gives you effective dissipation. It's not information that is really lost, but it's lost for practical purposes because it's lost to unobservable degrees of freedom. So understanding that process will tell us what is could allow us maybe to calculate what is the value of certain transport coefficients. That was the hope, but it turns out that it's not, you know, as simple as people thought. And so far, there is no known connection or very deep. Well, you could imagine that this there is a relation between the diffusivity, say heat diffusion constant. Energy is the most fundamental conserved quantity, and things you can calculate from chaos, because if you look at the dimensions, this has dimensions of length squared over time, right, which is like velocity times length. You can, or another way to say it, it's velocity squared times time. So you can say by dimensional analysis, you maybe expect that the heat diffusion constant will be related to VB over lambda, the Altman exponent. And indeed, it works in some systems, but it turns out that not always. Maybe in very generic systems, it works, very, very generic, but there are certain cases where it definitely breaks down. So, I won't talk about that. It's not going to be the focus of my work. So the main of what what I want to say, what I want to talk about in the rest of this lecture is scrambling in random unitary circuits. And what I'll talk about now can be found in this paper by Adam Nahum, Vijay, and Ha. And also there is a parallel paper by these guys, but mainly I want to talk about a mapping to a spin model that appears in this paper. So let me kind of mainly follow their approach. And the basic idea behind both of these papers is that we want to simplify the calculation of dynamics. Quantum dynamics is something really complicated, and we don't know how to calculate dynamics. We don't have any tool like even Monte Carlo to calculate dynamics. We have phases, it's super complicated. The idea is to simplify the calculation of dynamics by giving up the hope or the ambition to calculate a particular dynamics of a particular system, but really look at the dynamics averaged over a random ensemble of different systems. And this random ensemble that is the simplest one is an ensemble of that is composed of random unitary gates. Okay, so for example, the simplest geometry is this 1 + 1 dimensional geometry that I draw here, called brick wall geometry, where I have 2 qubit gates or 2 qubit gates. In general, I can have q degrees of freedom coming in and out of every line. Okay, when I draw this thing, by the way, if I draw something like this, that means an operator. In this case, these are unitary operators. These are the input qubits at the bottom and output qubits at the top. Okay, so I hope this is understood. And the hope is that, first of all, we can simplify everything by averaging over this ensemble. And then we hope that we capture universal properties even of systems that are not really described by this kind of ensemble, like Hamiltonian systems. That's more of a stretch, right? Because this doesn't have energy conservation. It's really not Hamiltonian dynamics, but it is very relevant, for example, for quantum circuits that you find in quantum computers. Not that there are any quantum computers, but when we will have quantum computers, they'll probably be made of some large networks of unitaries. And if I want to look at their generic properties, I don't know what gates I put in, I can average over all possible gates, right? In fact, quantum computers probably will include more elements like measurements, for example, and errors. And we'll talk about this separately. For now, let's look at unitaries, which are the most the simplest elements. And the first thing we want to ask is, since we talked about this operator growth, we can ask about how do we describe operator growth in that circuit. And again, we define it in exactly the same way. This is the out of time order correlator, but we average that correlator after the fact by over all the possible unitary circuits. I want to say something, that what we'll find actually is that the simplification is going to be that we will be able to transform from needing to calculate some unitary dynamics, which is very, very hard. After averaging, we'll map the system to an equilibrium statistical mechanics model, which is much easier to handle, okay? Or at least we can handle with more standard tools. That's the idea. So now we're going to calculate the average out of time order correlator. And to simplify everything, we can use the operators here. O, that's the operator that we let grow, and Y is what we called before the probe operator that is static. We take them to be generalized Pauli operators in the sense that they square to 1. If that's the case, then when I open these commutators, I'll have two parts, one that will have them both squared to 1, so I'll just get 1, and the other is this out of time order piece. And so I'll just get 1 minus this thing, okay? And my goal is to calculate this 1 minus out of time order correlator, okay? And the rules of the game are that in this circuit, every unitary here, for example, unitary at x and time t, is chosen from an independent uniform distribution on the Haar measure, which is basically the measure of integration over the Lie group manifold of, say, U2 group manifold, because this is, well, it's not U2, it depends on number of, the degree of the qubits, but this UN group manifold. Okay, so how do we map to a spin model? So let me go a little bit slowly here. Let me draw, first of all, schematically, the out of time order correlator. So first of all, just look at this figure. So this schematic figure is basically drawing this correlator. So what happens here? Let's start from let's start from this O of t at the bottom. Okay. So what we calculated is we have, because it's O of t, it has U applied on two sides, U dagger on the bottom, U on the top. Okay. And then we have Y. And then we have another O of t. So we have U dagger O U. Right? This thing is the operator O. It acts on 1 qubit, right? So we draw it like this. This is operator Y. It also acts on 1 qubit. And these boxes are just the code for an entire thing like this, right? An entire brick wall circuit. I just don't draw it all because it's too complicated. And then after everything, we need to trace, because we look at infinite temperature. It's tracing the infinite temperature density matrix is proportional to the identity. So we just trace. Okay, so this is what we want to calculate. So now the first simplification is, instead of looking at this not so nice tower, let me collapse it by folding it like a blanket, right? So I'm going to fold it so that first of all, I'm going to fold it with this U and U dagger. They're going to fold so that the Y's will be at the top, right? And then I'll fold also the next U and U dagger. And what I'll get, you need a little bit of geometric imagination. What I'll get is this. I'll get 4 such unitary circuits on top of each other like this, right, after the folding. And the lines connected in this way. On the top, you see all the lines are connected. Let me number the systems here. You see there are 4, the system is replicated 4 times, but one time it's U, one time it's U dagger, another time it's U, another time it's U dagger. Let me call it 1 bar, 2 and 2 bar. So there are 2 systems, and each system has forward in time and backward in time representative. Okay, so I give them colors blue and red here. So this is 1 bar, 2 and 2 bar. You see that at the bottom where O is, we always connect 1 with 1 bar and 2 and 2 bar, right? When I have a connection like that, that means matrix multiplication, summation over the same index, right? And so we have these, I tried to draw, not so well, but I tried to draw that everywhere we connect the circuit like this, there is one special point where we connect and put the operator O naught where we connect, okay? And the same thing and the top. And this whole thing gives a number at the end, right? Because it's basically, we contract this whole network and it should give us a number, which is this, okay? And the goal is to calculate this number. Here is another way to draw it, which is even simpler. And also shows the fact that each one of these squares actually has many internal squares, right? Each one of these squares is really this network.
I have a quick question here.
Yes, sure.
The quantity on the left that you wrote, the trace thing, is that OTOC that we wanted to calculate? What is that quantity?
Yeah, this here, it's the OTOC that we wanted to calculate. Remember, this is the OTOC. I haven't done the average yet. So far, no averaging. But yeah, this is the OTOC. You see it here. It's this. Now I open it. When I open it, I'll get two types of contributions. One type will always look like that. Another type will look like OOYY or YYOO, and this is one.
Mm-hmm.
Okay, so I simplified it a bit. They simplified it a bit by taking such operators that always square to 1, so this thing can be 1, and we can only worry about this.
And O and Y are both only single side; they're not strings.
Yeah, O naught at times 0 is not a string.
Mm-hmm.
Okay, but O naught, the squaring to 1 is preserved by the unitary evolution. So O of t squared is also 1.
Okay.
Okay, so yeah. So what I calculate now is just this non-trivial part of the 1 minus f. I'll return 1 minus this of the OTOC. So it's not the full OTOC yet. Okay, and so now I draw it in another way, which is just explicitly shows you this brick wall structure. This is this, and the fact that there are 4 lines coming out of every output and input point of the unitary is that these 4 lines correspond to, because the system is replicated 4 times. So there are 4 times. So here is zooming in, and you see what these 4 lines mean really, right? There is U star, U star on every point like that. This is the local use. And at the top, the lines are connected in this way that system 1 ket is connected to system 2 bar, right? And 2 is connected to 1, right? That's this thing. I call this swap because the 2 systems are swapped. Right? Instead of connecting system 1 to system 1, I connect system 1 to system 2 and system 2 to system 1. This is called swap. And at the bottom, I have this connection, which is, I call identity, because it's like a trace. System 1 is calculated, it is connected to system 1, okay? Still, this looks like a really complicated tensor network to contract. It's basically as hard as calculating the full dynamics of a system. You know, I can always, any dynamics of a system, I can draw like that as a tensor network. It's not going to make it any easier to draw, to calculate it. It will be an exponentially hard task, right? So how do I simplify that? Luckily, when I average over the unitary, so I want to average, I want to now integrate over this Haar measure, this thing, and I want to, and I'll get a new operator, which is the average over all the possible unitaries, but still I need to get an operator that operates in this kind of enlarged Hilbert space of, you know, quadrupled Hilbert space, right? If we had H before, now our new Hilbert space on which the operator acts, of states which the operator acts on, is quadrupled into the state of, you know, Ketz, Braz, times kets times bras. And I'm still going to get an operator that acts in this space, but I claim after averaging, it's going to be a much simpler operator, which will allow me to contract the tensor network efficiently. Okay, so let's see, what is that operator? What happens when I average over this unitary? I can look at each one of them independently because I have an independent average over them. I'm not going to show exactly. If you want, I can motivate it a little bit if you ask, but if I do this averaging, what happens is something very simple. So it stays an operator in the same Hilbert space, and these sigma and tau are states in this enlarged Hilbert space. And it looks like this, but the sigma and tau are very special states in this Hilbert space that I'll tell you what they are. W sigma tau is some function called the Weingarten function. This is for doing this for a single unitary is something that's known in the quantum information community. And the nice thing about this paper, it gave us a very, very nice representation in terms of spins, and that allows to connect it in a network also. So here is how I can interpret this thing. I can interpret this as having sigma and tau run over not all the possible states in the Hilbert space, right? There are 16 states in the Hilbert space, right? Because we have, it's a unitary acting on 2 qubits. Well, not 16, well, for 2 qubits, it's 16. For qubits, it's 16. For qubits, it's q to power q to the 8 or something, right? Or q to the 4th. So yeah, q to the 8. No, q to the 4th power. The size of the Hilbert space, but you see here the only states that appear are 2 states, sigma and tau. So the whole tensor network that acts on this huge Hilbert space is simplified to a tensor network that acts in a space of 2 states, which I'll say what they are. So what I get is this, and I can represent this diagrammatically nicely as each unitary looks like 2 classical spins, classical degrees of freedom that can get the value sigma and tau, and sigma and tau, and these states, sigma and tau, I represent them as being either up or down. The tau, let's look at the ket state. It's up or down. It's basically a tensor product of states of, say, qubit 1 and states of the other qubits from the output legs of the unitary. And these states, when it's up, these states are simply the states that symmetrize, that are basically identify ket and bra of the same system, right? So this is ket and bra AA. So this ket AABB is AABB for these systems, and you see that I force the ket and the bra and the ket and the bra of same system to be the same here, right? So these are these states summed over A and summed over B, and the state and the same for the other leg, CCDD, right? These are the only states that remain here. And the down state is the state where I swap, right? I take A and A, the states are identical in the ket and bra of the the ket and the bra of the two different systems, system 1 and system 2, right? And the same here, right? This is the down state. And I can represent it graphically like this, right? So here I identify ket and bra of the same system, and here I identify ket and bra of the opposite systems. This is called identity, and this is called swap. Okay, this is how it looks graphically. This state, this is the state up, this is the state down, and this is the same for the bra. Okay, and the Weingarten function is this. It's simply this thing. It's 1 if sigma equals tau, and it's -1 over q squared. Q is the number of states in the qubit. And now we want to understand what happens when I need to contract the tensor network. I want to know what happens when I couple to another unitary. When I couple to another unitary, I get easily, you can see that basically you need to contract like this. So if I have minus and minus, for example, then minus looks like this here and looks like this here. And I need to contract them. I get 2 loops. Each loop gives me a factor q squared, and I get 1 over q squared from the normalizations here, here, and here. So I get 1. And the same if I have plus and plus, it would be just 2 disconnected loops like this. But it's the same scaling. But if I have plus and minus, or up and down, up and down, then I have to contract something like up is this with something like this here, and I get a single loop. So I get a single sum over q times the normalization, I get 1 over q. So now we can reinterpret this contraction of the tensor network as we have to sum now over all the possible values of sigma and tau, right? And we need to, and each one of them gives us some weight. And that weight can loosely be interpreted as a weight in a partition function with Boltzmann weights, and we just calculated them, and they depend on the spin-spin, 2 spin interactions. There are 2 spin interactions inside a unitary because we have 2 spins inside each unitary, and we have spin-spin interactions between unitaries, and we know all these Boltzmann weights. There are just 2 problems, and it all lives, if you now draw it, the brick wall circuit now looks like a hexagonal lattice with spins sitting on its vertices. There are just 2 problems, and that is that we got negative weights in the Weingarten function, so it's not really a classical partition function, and also that I didn't tell you what to do with the top and the bottom boundaries. So here is the solution, first of all, of problem 1. It turns out that I can actually solve this by integrating out exactly the spins, either the top or bottom spin. So I can integrate out all the sigma spins exactly without a problem. And then I get a new model with only the, say here, I call them tau, I guess, only the tau spins. And now they sit on a triangular lattice because I killed all these. So now what I have left is a triangular lattice. And this triangular lattice has new interactions, and I won't calculate them, but you can look at the paper and see it's tedious, but not hard in the end. The interactions are kind of strange. So what we get is an Ising ferromagnet on the triangular lattice. There is Z2 symmetry, and we can discuss for a second what's the origin of this Z2 symmetry. And it's a Z2 symmetric Ising model, but with strange interactions that I can phrase as 3 spin interactions only on upward triangles, no interactions on downward triangles. And the interactions look like this. Configuration like this, S prime, SS on a triangle, it must have all spins the same here. So there can't be a downward triangle with spins different. The reason now that I have only downward triangles and not up triangles is because I chose to integrate out the tau. If I did the opposite, I'll get, of course, the opposite. So there is no breaking of this symmetry here. It's really because of this, the way we integrated out. Now, another rule is that if we have a triangle like this, we can have 2 S's the same here, and then the other S not equal to these two. And then we get a Boltzmann weight a weight that looks like this. Note that if I take Q to infinity, this is very strongly suppressed compared to the top configuration. Okay, so what does this mean? So now it's an Ising ferromagnet. You see that it really likes having all spins the same, right? This is the smallest Boltzmann weight I get is if all spins are the same. Anything else, you can think of this as a seed of a domain wall, right? Because we have a domain wall running through here where this would be, say, a down spin and these are up spins. And here you see that the domain walls can be only in 45 degrees. They're in 45 degree segments. Well, yeah, some 45 degree segments like this. But they can turn right or left freely. And you pay some energy cost, some Boltzmann weight cost for this length of a domain wall. But importantly, they cannot turn back. You cannot have a domain wall. You cannot have closed domain walls because you cannot turn back a domain wall. Why you cannot turn back a domain wall? Well, if I turn back a domain wall, I'll have a configuration at the tip where I have a up Ising spin, down Ising spin here, down Ising spin here. And you see from here that this is not allowed. Configuration S prime SS must have delta SS prime. So it has 0 weight, this configuration. So I cannot have a turning back, right? This does not allow turning back. Good. Any questions? Yeah, I see. I don't have much.
I have a question.
Yes.
Can you explain again, like how you came up with the triangular lattice from the hexagonal?
I just eliminated the spins in the top and the bottom, and if you integrate over them,
integrate.
Right? Okay. Yeah, you integrate over them, and then you get a new model. To see how it's done and why it's kind of simple there, I didn't tell you the exact rules. Well, I did, yeah, but here the rules are sufficiently simple that the couplings that allows you to integrate out exactly. And when you do that, you get these 3 spin interactions that still maintain, of course, the Ising symmetry. They have to maintain the Ising symmetry. Now, the Ising symmetry is actually pretty obvious that you have to have it because really, remember what happens here is this four systems basically propagate states like this, identical states. Or they can propagate whatever you do. So you have this evolution UU star, UU star, and you can permute this evolution is symmetric with respect to permute taking all the kets globally from the first system, from copy 1, in permuting with copy 2. So this evolution commutes with the swap operator, which takes J of copy. Let me write it like this: unit matrix IJ unit matrix. This is the swap operator. Okay, it swaps kets sum over IJ. Okay, this is a swap operator, and this because all these unitaries are identical, this commutes with the swap operator. So this dynamics commutes with swap, and swap is like a Z2 transformation. So there is a global Z2. It commutes with swap of everywhere, right? I need to take the product of all these swap xt. And that commutes with my my dynamics, and it commutes also with the averaging. So I have to have this Z2 symmetry, and this Z2 symmetry for swap is exactly the Ising symmetry that I get here. So I need to have that symmetry. If I had errors which made, for example, the unitary is not identical to each other exactly, that will break this swap symmetry and introduce, say, random magnetic fields in the up or down direction, depending on where the error occurs and how I can break this symmetry and introduce some random magnetic fields by introducing noise. But if I don't have noise, if my experiment knows how to take back and forth time with exactly the same unitaries, then this is a symmetry. Okay. So I have this domain wall, allowed domain walls, and now I can start to compute that. One thing I didn't talk about yet is the boundary conditions. This is taking me longer than expected, than I should have expected. The boundary conditions are, you saw what the boundary conditions are if you look at it here. So forget about the Y for a second. Everywhere away from this Y, the boundary condition is basically a swap at the top, right? The top is basically fixed to be a spin down, and you have to now contract with that. And the bottom, exactly similarly, is an identity, which I called a spin up. So it's the Ising model in the bulk, but we have boundary conditions of down spins at the top and up spins at the bottom for calculating this operator. It turns out that for calculating other things like entanglement entropy, for example, you need exactly the same kind of network of 4 copies, and you get exactly the same spin model, but the boundary conditions are different for the entanglement entropy. And for another situation that I hoped to get time to discuss, you'll get yet different boundary conditions. So depending on what quantity you want to calculate for situations where you need 4 identical unitaries, you will get different boundary conditions. For this autalk, the boundary conditions you have are all down at the top, all up at the bottom, and where the operators are, it's a little bit complicated. And but in the end, it turns into something simple if you calculate not this, where is it? Not this, but the whole thing. For the whole thing, 1 minus this. the boundary condition turns out to be very simple. It's the same everywhere, but it's for the operator O here, it forces a downspin above it. And for the operator Y, it forces a downspin below it. Okay, so this is basically the boundary condition. And now you can ask, what is the auto? So if I put Y somewhere very far here, so I have a downspin here, and I want to ask, and I have a downspin here, and I want to ask, what is the partition function? The problem now is this downspin can propagate a domain wall, right? I can have this downspin can propagate a domain wall in 45-degree angle, and no more than that, right? So in the end, what I'll have is I'll have upspins here all the way to downspins here, and that will be, I'll get a null partition function. So the partition function is going to turn out to be 0. On the other hand, if I have, so there is no auto for this situation. Auto is simply 0. However, if
I have a
Y,
quick question here.
yes.
So what happened to the negative weight Boltzmann weights that we had earlier before integrating
The negative Boltzmann weights that you had earlier in the W. Right, the negative Boltzmann weight in the W became positive weights when you integrated out these spins. Exactly. So for integrating out exactly, you don't care about the weights. You just they can be eliminated exactly. You can just sum over them.
I see. And if we had integrated out the
top
tau's
spin,
rather than the s's, then
what?
So we integrated out the not the sigma but the tau, or like the.
We could have integrated out the other, and then we'd get essentially the same rules but inverted downward, because unitaries are reversible. So we would have exactly the same, and all our conclusions would have been the same. Except it's like, actually, it's identical to choosing Y to be at time 0 and then O at time minus t, right? And doing this kind of choice is like taking O to be at time 0 and Y to be at time t. So basically, O is the one that propagates, and Y is the one that's probing. But it's identical. We could have looked at it the other way around, right? In unitary dynamics. If it was not unitary, then not necessarily. And what this, so now you see what's the meaning of this fact that in this special model, Ising model, you can only have domain walls that propagate on these segments of 45-degree segments. That forces kind of a light cone effect. Right, so and that's what you expect from unitary dynamics. So we could have expected that. So now the first time, yes.
There's another question in the chat.
Yes.
Says, could you explain the intuition why inserting O0 and YX results in a downspin right above or below?
Yeah, first of all, it has to do some perturbation to the boundary conditions that you have. It's not so simple, and the reason it's not so simple is that it's not for the it's not true for what if I look at the actual boundary conditions for not C of X and T, but for this original thing, the original. Where is it? For this, then actually I have a very well-defined boundary condition there, which is a Boltzmann weight, and it's a negative weight again. So I didn't want, but in order to get rid of this negative weight, you can actually note that you can calculate 1 minus this, and that eliminates all the configurations in the partition function that would actually have a negative weight. And the ones left that have a positive weight are always ones, basically the negative weight you get is for having a spin up there. So you can have a spin up, and in the original thing that gives you a negative weight, but when you calculate, when you calculate 1 minus that, it somehow gets canceled. So you get, in the end, you get, for 1 minus f, what you have is the only configurations that give you a non-zero weight in the partition function that don't cancel because of some cancellation are the ones where you have a downspin here. So that's how it comes in. But yeah, I'm sorry, I can't give you a really kind of really good intuition for this. This is the one thing here that really comes down to kind of a bit details there. Maybe I could if I thought a little bit more of this. But the important thing is that, okay, so let's accept that. If we accept that, then the first time we get a non-zero weight in the partition function, and we can get a partition function that actually obeys all these rules, because if I have a downspin here embedded in all the upspins around here, because I can't reach with the domain wall, then I'm bound to disobey this rule 1, right? I will have a domain wall with a tip. So in order to have a non-zero weight, I need to have y inside this light cone, okay? Which makes sense. This is the light cone effect. Now, when it is inside the light cone, if it's just inside the light cone, there is just one domain wall that will be fine. It will be this blue domain wall. But if it's more inside the light cone, then I'll have more domain walls that are fine. This green domain wall is okay. And this, anything that actually, so there are many domain walls, and it's easy to count them. It's very simple combinatorics to count them and calculate, then calculate this partition function. So there are two things that contribute to this partition function. There is entropy due to the number of configurations of domain walls that end at the same point. And then there is energy cost, because here you will have spin downs, and here you will have spin ups. Here you will have spin up where the domain wall still hasn't reached. You will have spin up near spin down. That will cost you that will give you an additional energy cost. So there is now a partition function with energy term and an entropy term that looks like a random walk, the entropy term, and it's a biased random walk. And in the end, what you get is a domain wall structure that basically gives you a probability distribution around some mean velocity, and that probability distribution, because of this random walk of the domain walls, is expanding diffusively. So what you get is a structure of C, X, and T that has a front that grows. So it has a strictly zero above some V, let's call it V naught times T. And then it has some V butterfly times T. This is X. And it has a width. This looks like an error function, which you can calculate. And it has a width of order, so let's call it sigma squared, is proportional to some diffusion constant times T. So it's, and diffusion constant is, well, it's something of order 1. So there is a diffusing size of this front, and it propagates at some velocity. this is really a nice result you can get from the spin model. You can get it from other considerations. The nice thing about the spin model, it's very powerful to get you get many other properties. So I think my time is up. I was going to talk about Hayden-Preskill experiment. Maybe just let me say what it is. I won't have time to really explain it thoroughly. I have 2 minutes.
Sure.
Yeah, so Hayden and Preskill frame it as a kind of a nice story with a black hole and all that, but all it is some unitary, big unitary that is sufficiently randomizing, that scrambles. For them, they say, okay, it's a black hole because it's a fast scrambler, but it doesn't have to be. There is this unitary, and the question is, if I'm Alice and I have some diary that I want to hide, so I take my diary, it has a small number of bits, say k bits. So I want to take k bits and encode a wave and throw in a wave function psi into these k bits. And here the rest is n minus k bits. So together they're k bits. And because this is a scrambler, she says, well, nobody is going to ever be able to read my diary because it's I scrambled it with this enormous unitary. She's using what we learned. Scramblers do bad things. Well, she doesn't know that actually these n minus k bits came from entangled bell pairs where Bob holds n minus k partners of these bits. Okay, he holds them. Okay, and now the question is, if you can think about it, if this is a black hole, then Bob holds the other n minus k bits because he got the Hawking radiation from the evaporation of the black hole before it reached the stage that Alice throws the bits inside. So that's why he holds all these entangled pairs. He didn't read them, but he has them. And now the question is, after this evolved for some time, now how many bits of Hawking radiation does Bob need to read? And the rest, he doesn't care. He can discard the rest, can go to anywhere. How many does he have to read in order for the information, to have all the information about the diary, Alice's diary? And the answer is, it's enough for him to read k plus a little bit, let's say k plus c bits. So he needs to measure k plus c bits where k is small. K is 10 bits diary, and the black hole is 10 to the 200. So he doesn't have to read the entire black hole. He just needs to read a few bits. And because he also has this large number of bits here that are entangled with the black hole, it turns out that all the information about this diary is in here. Now, this is that's where Hayden and Preskill stopped. It already sounds a little bit mysterious, right? Because how come? I mean, I threw so many bits. I threw here n minus k minus c bits, which is a huge number. C is small. Huge number of bits I threw away. How do I know that I didn't pour Alice's information with that, right? This sounds a bit strange. It turns out that no, I can be certain of that. And the reason is the scrambling. And the key is a very important theorem in quantum information that has to do with scrambling and thermalization called the decoupling theorem. And let me bend Alice's wave function all the way here. And the decoupling theorem tells us that if we have, let me draw it in a kind of a more formal way. Yeah. Sorry. This is some environment. This is A1 and A2. And now suppose I discard A2, A2, and I want to ask about the density matrix of A1 and E. It's a reduced density matrix here. Here I have, there is a number of bits here, there are a number of bits here, there are a number of bits here. Here, A1 and E are somehow entangled. You can think of E as the environment, and there has been some decoherence. So there was a channel here, an entrance channel here, but it got entangled with the environment at some point. Somewhat entangled with the environment. And now we can ask the question, what is the density matrix A and E? And there is, the decoupling theorem tells us that if A2, the size of A2 is, I'm saying it very roughly now, but if the size of A2 is larger than the size of A1 and E combined, the total size of the Hilbert space times A2 over 2. If it's larger than that, if A2 is more than half the total system, then
Sorry,
yeah,
should there really be an A2 on the right?
Yeah. Sorry, what?
Should there really be an A2 on the right?
A2 is here.
No, in your equation, you have an A2 on the left and the right of the inequality.
Yeah. A2, the size, yeah, you can, let's see. So another way to say it is A2 should be larger than A1 times E. Yeah, sorry, yes. Right, yeah, then the rest. So A2 is larger than the full Hilbert space. The Hilbert space of A2 that I lose is larger than A1 times E. In this case, the density matrix is simply the maximally mixed density matrix of A1, times some density matrix of E. So they're completely decoupled. So all the correlations that existed between A1 and this system A, so all the correlations, between E and A are now between E and A2. No correlations between A1 and E. Okay, up to some corrections of the order of the size of the Hilbert space. So you can think about it as thermalization. If this is smaller than the entire system, then you can think of A2 as being a bath. And now you're in, because U is fully scrambling, then A1 and E should have zero correlation because it's an infinite temperature state. The bath is basically put them in an infinite temperature state. So that's kind of the proof, physics proof of this theorem. And now basically we can use this theorem and see that this system that Bob holds is larger than half the entire system. So, and therefore, actually, all the correlations between A and this system have been lost. So A and the thrown away system are effectively uncorrelated. So all the correlations, all the Bell pairs are shared with the system that Bob has in his hand. This is basically what the decoupling theorem, which is basically just thermalization, tells us. That's what Alice didn't take into account and Bob made use of. But now what Hayden and Preskill said, well, what I did now is a bit problematic. Okay, so it's clear he has the information, Bob, but can he decode the information and find what is Alice's? And that's, no, you could say that's not trivial. And they postulated that, well, they didn't know if it's possible or not to do it easily. And it turns out you can. About 10 years later, after this paper, Yoshida and Kitaev showed an efficient decoding algorithm. And this decoding algorithm is actually very simple, but to show it works, actually,
because of the time, we should wrap up really quickly. So if this is quick to explain, go for it. But otherwise, maybe we could talk about it more in the questions.
Okay, yeah, we can talk about it in the question period. I can explain it more and how it's related. I mean, there is a decoding scheme, and you can prove the decoding scheme works easily by using our spin model analysis. And even you can prove it that it works and when it works, because if you can prove that it works even for unitaries that are completely local and brick wall structure, and you can show how deep they have to be so that this decoding scheme would actually work. And the spins give you kind of a beautiful view of this that shows that when it works. And it can also show what happens when I turn on some errors, which in the Ising model are like local magnetic fields. Okay.
Great. So thank you very much for all three of your lectures and today's lectures. So let's take some questions. Well, I do want to make sure everyone gets a break, but please ask your questions now.
Yeah, I have a question about the local unitary decomposition.
Local what? Unitary?
Yeah, just the unitary decompositions of the type of evolution operators.
Yeah.
Yeah, I'm not sure. Is that proved to be exact for the local driving Hamiltonians, that this local decomposition is exact?
Which local decomposition are you talking about here?
I think it's actually at the beginning. Could you please just, yeah, that's, no. That which you.
Which decomposition?
I think it's the section of the, let me see, scrambling in the random unitary circuits.
Okay, yeah.
Yeah, this red picture.
Yes. So what is exact?
In this decomposition of the type evolution operators used here and after.
This is the model. There is no exact or not exact. It's just, this is the model. It's not going to, it's not trying to simulate a Hamiltonian dynamics. It's just a different model of dynamics. It's a model where every, it's just a model where you have a set of qubits and they're evolved by a set of gates. And the gates are just chosen completely randomly out of a uniform distribution. And uniform distribution for unitary gates is uniform on the Lie group of the unitary group, right? On the manifold of Lie manifold of the unitary group. So it's just a model, right? There is nothing exact or non-exact. It's just the that's a model we want to calculate. Now we can ask how does it relate to Hamiltonian dynamics? Of course, it's different than Hamiltonian dynamics. It doesn't have energy conservation, for example. There is no sense of energy conservation. I would expect that it's the same universality, for example, as a time-dependent Hamiltonian dynamics, where your Hamiltonian has some random time dependence. That we expect, although it's not exactly the same, we expect that it would be based on symmetries, that it would be the same universality class.
So it's just an expectation that we want it to be of the same universality class, but we are not sure.
Yeah, but this is essentially what we always do in physics when we try to find universal phenomena. So it's basically the same philosophy as random matrix theory, right? Random matrix theory doesn't describe really Hamiltonians, chaotic Hamiltonians, but we use random matrix theory and we find a lot of properties, and all of these properties seem to be correct also for chaotic Hamiltonians that are non-random, if they have the right symmetries for that ensemble. So you can think of this as generalization of random matrix theory, where now we have kind of a local random matrix theory. And of course, it's not going to describe a local random matrix theory because every unitary here is like a random matrix. And now we have some spatial structure and propagation. So it's kind of more powerful than random matrix theory. It also, we look at quantities that often people don't look at in random matrix theory because they involve 4 unitaries and not just 2 unitaries. But apart from that, it's very similar, and the kinds of manipulations are similar to random matrix theory. And yes, the hope is that it captures something universal. That, for example, this time evolution of the if we don't have any conserved quantities, then we capture something universally correct about the time evolution of operators, as long as we don't satisfy these. Remember, I have a criterion for when we should have exponential growth of the OTOC, and if that criterion holds at least for some time, then for that time scale, this universality is incorrect. But there is a time scale which we call scrambling time. When we reach that scale, then everything becomes maybe more universal, and this holds, right? But again, yeah, there is no map. It's not designed to be a mapping from any kind of specific physical system, but it's an average over an ensemble of physical systems that hopefully captures some universal properties.
Yes, I'm
Great.
also just wondering.
Well, so I hate to cut this off, but we have a very, very short break now. And I know other people have questions as well. So I'm going to encourage you to take all of those questions, save them up for the recap this afternoon. And Ehud, I believe, will be at the recap.
I'll be there. What time is it? It's 2 p.m. in Boulder time?
2 p.m. Boulder time. Let me just confirm. Yeah, it's 2 p.m. Boulder time, Mountain time.
Okay,
and so we can continue all of this discussion. We'll have plenty of time for questions then. So again, sorry to cut you off, Haltian, and others who wanted to ask questions.
No
Thanks again, Ehud, and looking forward to continuing this afternoon. See you soon. Bye-bye.